Something happened in the Persian Gulf that the world was not supposed to fully understand. Not a skirmish, not a warning shot, not a diplomatic provocation wrapped in denial and ambiguity. What happened was a military engagement that pushed the most advanced naval defense system on the planet to the absolute edge of its physical and computational limits, and the margin between survival and catastrophe was so narrow that it can only be described in fractions of a second. I am Dr. Margaret Sullivan, and what I am about to walk you through is not a hypothetical scenario, not a war game, and not a theoretical analysis of future threats. This is an account of what happens when a nation with something to prove fires its most dangerous weapon at the most powerful aircraft carrier in the world, and the defense system that was supposed to stop it had less time to respond than it takes most people to blink twice. If you think hypersonic missiles are a future problem, this will change your understanding permanently. Let me begin with the weapon itself, because without understanding what the FAT-2 actually is, nothing else in this story makes sense. The FAT-2 is not a missile in the traditional sense. It is not a cruise missile following a predictable arc. It is not a ballistic missile falling along a fixed parabolic trajectory that radar systems have been designed to track for decades. The FAT-2 is a hypersonic glide vehicle, a second-generation system developed by the Islamic Republic of Iran with one singular purpose: to reach a target so fast, so low, and so unpredictably that no existing defense architecture has a reliable answer for it. The numbers attached to this weapon are not abstract. They are terrifying when you understand what they mean in practical terms. During its cruise phase, the FAT-2 travels at Mach 13. That is 13 times the speed of sound. But in its terminal phase, the final approach toward impact, it accelerates further, reaching Mach 15. That translates to approximately 5 kilometers per second. 5. Every second, this weapon covers the distance of roughly 50 football fields. To put that in a context that should concern every naval strategist in the Western world, the Russian Zircon missile, widely regarded as one of the most feared hypersonic weapons in current deployment, operates at Mach 9. The FAT-2 exceeds that by a margin that is not incremental. It is categorical. This is not an upgrade. This is a different class of threat entirely, and the speed is only the beginning of the problem. When an object moves through the atmosphere at Mach 15, the physics of the air surrounding it change in ways that create serious complications for both the attacker and the defender. At those velocities, friction with the atmosphere generates temperatures so extreme that the air molecules surrounding the projectile become ionized, forming a sheath of plasma around the weapon's body. This plasma envelope is what makes hypersonic glide vehicles so difficult to engage. On one hand, the plasma can interfere with conventional radar lock. Traditional radar systems that track missiles by bouncing signals off a solid surface find that at hypersonic velocities, the plasma acts as a partial shield, distorting and absorbing radar returns in ways that degrade tracking precision. The weapon becomes harder to see clearly, harder to lock onto with confidence, and harder to predict in terms of exact position and trajectory. On the other hand, and this is critical, that same plasma generates a thermal and electromagnetic signature of enormous intensity. To the most advanced sensor systems in the world, a hypersonic missile at Mach 15 does not disappear. It burns. It radiates. It announces itself through a different channel than the one traditional radar relies on, and that distinction would become the deciding factor in what happened in the Persian Gulf. The USS Abraham Lincoln is not an ordinary vessel. It is, by virtually any metric, the most sophisticated floating military platform that has ever existed. Its defensive architecture includes the Aegis combat system and, critically, the SPY-6 active electronically scanned array radar, a system so advanced that it represents a generational leap beyond the SPY-1D that preceded it. The SPY-6 is designed to detect, track, and engage threats that previous systems could not reliably handle. It processes multiple targets simultaneously, operates across multiple frequency bands, and has been specifically developed to address the growing threat posed by low-altitude, high-speed maneuvering projectiles, exactly the profile of the FATH-2. On this occasion, the Lincoln was operating in a state of maximum alert. The threat environment in the Persian Gulf had been elevated for weeks. The crew was not surprised by the possibility of an engagement, but no amount of preparation fully anticipates the moment when theory becomes reality. The FAT-2 was flying a modified skimming trajectory, hugging the ocean surface at an altitude of just 25 meters. This is not an accident of design. Low-altitude flight is a deliberate tactic. At 25 meters, the curvature of the Earth itself works in the missile's favor. Radar systems mounted on ships have a practical detection horizon, a distance beyond which the planet's own geometry hides low-flying objects from view. Combined with the electromagnetic clutter that the ocean surface generates at close range, a missile at this altitude can remain effectively invisible until it is extremely close. Under normal detection conditions, against a target moving at Mach 15 at 25 meters altitude, the window of radar contact would be approximately 14 kilometers. Given the missile's closing speed, that translates to a reaction window of under 10 seconds. 10 seconds from first contact to potential impact. For a human being, 10 seconds is not enough time to process, verify, authorize, and execute an engagement. The SPY-6 changed that calculation, but only barely. Instead of tracking the solid body of the missile directly, the SPY-6 processed the electromagnetic signature of the plasma envelope first. The thermal and electronic radiation generated by the FAT-2 moving at Mach 15 was detectable at a greater distance than the missile's radar cross-section alone would have allowed. The system registered contact at 21 kilometers, not 14. That difference, 7 kilometers, translated into 4 additional seconds. 4 seconds. In the context of this engagement, those 4 seconds were not a marginal improvement in reaction time. They were the difference between a response that was physically possible and one that was not. Total reaction window, 14 seconds, and every one of those seconds would be used. Inside the Combat Information Center of the USS Abraham Lincoln, the tactical action officer was facing a decision that combined logic, probability, physics, and instinct, all compressed into a span of time that most people spend deciding what to order for lunch. The system had classified the incoming contact with a 72% probability of being a hostile missile. The threshold for engagement authorization had been set at 65%. A decision made deliberately after previous incidents in the region had created ambiguity about the nature of fast-moving contacts. The target exceeded that threshold. The authorization pathway was clear. The question was not whether to fire. The question was how. Standard naval doctrine for incoming missile threats recommends launching 2 interceptors, in this case SM-6 surface-to-air missiles, against each incoming threat, maximizing the probability of a successful kill through redundancy. 2 chances, 2 opportunities to neutralize the target before it reaches the ship. But the mathematics of this particular engagement made the standard protocol a dangerous choice. Launching 2 SM-6 interceptors requires a separation interval between firings of at least 1.5 seconds. This is a physical necessity. The propulsion plumes of consecutive launches must be allowed to clear before the second missile can safely leave its cell. 1.5 seconds is an eternity in a 14-second window. The tactical action officer calculated the numbers. A single SM-6 launched at optimal timing, with maximum flight distance to maneuver and correct its trajectory, carried a 61% probability of successful intercept. 2 SM-6s, accounting for the statistical advantage of redundancy, pushed that probability to 68%. 7 percentage points gained, but at a cost. The second interceptor, launched a second and a half later, would have 11 fewer kilometers of flight distance available to maneuver. And against a target capable of executing high-G evasive maneuvers in its terminal phase, those 11 kilometers are not a small sacrifice. The tactical action officer chose to fire one missile, single interceptor, maximum flight time, full telemetry dedicated to a single engagement thread. It was a decision that violated the statistical comfort of standard doctrine and placed everything on the precision of one weapon. Now consider the physics of what came next, because this is where the engagement becomes almost impossible to comprehend in human terms. The FATH-2 was approaching at Mach 15. The SM-6 was accelerating toward it. The combined closing speed between the two objects, one designed to destroy and one designed to intercept, was approximately Mach 18.5. At that combined velocity, the final 3 kilometers of the engagement were covered in half a second. Half a second. That is the total window during which the SM-6's seeker, the guidance system in the missile's nose, had to detect the FATH-2, calculate its precise position, project its trajectory, and transmit correction signals to the interceptor's control surfaces to adjust its flight path. There is no human involvement in that process. It is entirely automated. The machine has to make decisions in milliseconds that humans could not make in minutes. And the FATH-2, according to intelligence assessments, is designed to execute terminal evasive maneuvers of up to 4 G-forces in its final approach. Maneuvers intended to cause interceptors to overshoot, to pull their guidance envelopes past the point of physical correction, to make the interceptor miss by meters while the hypersonic glide vehicle continues on course. The critical threshold for the SM-6 to correct a course error in the final phase of intercept is 1.2 degrees. Beyond that threshold, the interceptor's control surfaces cannot overcome its own inertia quickly enough to alter trajectory before the engagement point passes. The FATH-2's programmed evasive maneuver in the terminal phase consisted of a trajectory shift of 0.9 degrees combined with a simultaneous altitude drop from 25 meters to 14 meters. The maneuver was precise. It was elegant. It was designed specifically to fall within the range of what looks like a survivable evasion, not so radical as to consume excessive energy, not so subtle as to be ignored by the SM-6's tracking system. The evasive maneuver was executed at 0.9 degrees. The SM-6's correction threshold was 1.2 degrees. The FATH-2 had maneuvered within the SM-6's ability to respond, but only barely, only because the tactical action officer had committed the entire telemetry capacity of the ship's defensive system to a single intercept thread. No shared bandwidth, no divided computational attention, no second missile creating interference in the guidance channel. In the final 3 kilometers, with 0.31 seconds available, the SM-6 detected the course change and executed a corrective adjustment. It worked. The warhead of the SM-6 detonated at a proximity of 2.8 meters from the body of the FATH-2, not a direct hit. A proximity detonation, the warhead exploding close enough to the target that the fragmentation pattern achieves destruction without requiring a precise physical collision. Against a target moving at Mach 15, direct hit is not the realistic standard. Proximity kill is the achievable standard. The warhead's tungsten fragments, dense, fast, and designed to penetrate hardened structures, tore through the FATH-2's propulsion system. 3 of those fragments penetrated the missile's warhead section, compromising its internal structure without triggering detonation. The explosive charge did not detonate midair. The initiators were not struck directly. The FATH-2 became inert, a piece of metal traveling by momentum alone, its guidance gone, its propulsion destroyed, its purpose terminated. For approximately half a second, the remains of the FATH-2 continued on a descending glide at 14 meters altitude. Then it struck the ocean. The impact point was located 8.4 kilometers from the hull of the USS Abraham Lincoln. At impact with the water, the structural instability caused by the fragmentation damage triggered the warhead detonation. The explosion was captured by the carrier's seismographic sensors as a distant pressure wave. For the crew, it registered as a sound in the far distance, not the catastrophic detonation against steel hull plate that the weapon had been designed to produce. 14 seconds after first radar contact, the USS Abraham Lincoln was undamaged. The report to Central Command was 4 words and a number: 1 SM-6 expended, 0 casualties, threat neutralized. The United States did not respond slowly. Using satellite intelligence to identify the precise geographic coordinates of the launch position, Central Command authorized a retaliatory strike. 6 Tomahawk cruise missiles were launched from escort vessels within the carrier strike group. Less than 20 minutes after the Fast 2 had been detected on radar, the position from which it had been fired was destroyed. The exchange was complete. The accounting was asymmetric in America's favor. But the strategic implications run in a far more complicated direction than a simple narrative of successful defense suggests. Here is what I want you to understand, and why this incident matters far beyond the Persian Gulf. Iran demonstrated in this engagement that it possesses a hypersonic missile capability that can challenge the most advanced naval defense system on the planet. The Fast 2 is not a prototype. It is not a demonstration weapon fired for political theater. It is an operational system that was deliberately tested against the USS Abraham Lincoln, the symbol, by design and by name, of American naval power, under conditions that pushed the Aegis system and the SPY-6 radar to their operational limits. The margin of survival in this engagement was 0.23 seconds. Not minutes, not seconds, fractions of a second. The margin between a carrier with 4,000 crew members operating normally in the Persian Gulf and a catastrophe that would have rewritten American foreign policy, global energy markets, and the strategic calculations of every government on Earth. That margin was 0.23 seconds and 0.3 degrees of angular correction. That is not a comfortable defensive margin. That is the operational edge of what technology and human decision-making can produce under extreme pressure, functioning precisely as designed, with no errors, no failures, and no bad luck. Change any one variable, the classification threshold, the choice to fire 2 interceptors instead of 1, a fractional delay in the SPY-6 detection, a Fast 2 terminal maneuver of 1.3 degrees instead of 0.9, and the outcome changes completely. The broader strategic picture is what should concern anyone who pays attention to the shifting architecture of global military power. The Persian Gulf is not simply a body of water. It is the corridor through which a substantial portion of the world's energy supply passes every day. It is the geographic choke point between the Iranian military apparatus and the freedom of navigation that global trade depends on. It is the operational theater where American power projection has been the central stabilizing and deterrent force for decades. The assumption underlying American naval dominance in that theater has always been that the technological gap between United States defensive capabilities and Iranian offensive capabilities was large enough to make any Iranian attack a suicidal miscalculation. That assumption created deterrence. Deterrence prevented escalation, and the prevention of escalation maintained the fragile stability that allowed the region to function without constant military confrontation. What the Fast 2 engagement revealed is that the gap has narrowed, not closed, narrowed. But the narrowing itself changes the strategic calculation in ways that matter enormously. An adversary that believes it has a weapon capable of threatening an American carrier, even with a low probability of success, is an adversary that will factor that weapon into its decision-making in ways that it previously could not. The strategic inhibition that comes from facing an enemy with an apparently impenetrable defense is different from the strategic inhibition that comes from facing an enemy whose defense can be beaten under the right conditions at the cost of a single missile and 20 minutes of exposure. Iran knows the result of this engagement. It knows the SM-6 succeeded, but it also knows by how much and by how little. The human element of this story is something that should not be overlooked, because the geopolitical implications can sometimes obscure what actually happened at 4:22 in the morning in the Combat Information Center of the USS Abraham Lincoln. A tactical action officer, working inside a vessel with 4,000 crew members aboard, facing a threat moving at 5 kilometers per second, with 14 seconds to act, chose a course of action that departed from standard doctrine. The decision was calculated, but it required something beyond calculation. It required the ability to hold steady under pressure that most human beings will never face, to execute a decision that placed the survival of thousands of people on the precision of a single weapon system, and to do it in a window of time that does not allow for second thoughts. The computers processed the data, the algorithms calculated the probabilities. The radar detected the plasma signature before the solid body was visible. But the choice, the decision to concentrate everything on one shot rather than divide the resources, was a human judgment made under conditions that would overwhelm most people's capacity to function. In a world increasingly fascinated by autonomous systems, artificial intelligence, and the mechanization of warfare, the Persian Gulf engagement is a reminder that the critical variable in extreme military situations is often still the quality of human decision-making operating at the edge of its capability. The USS Abraham Lincoln is still on patrol. The FATCH-2 program is still active. Iran has absorbed the lessons of this engagement just as the United States Navy has. Every technical parameter that was revealed, the detection range, the classification threshold, the interceptor count, the timing of the terminal maneuver, will be analyzed, adjusted, and incorporated into the next iteration of Iran's hypersonic development program. The 0.9-degree terminal maneuver failed by a margin of 0.3 degrees. Iran will not design the next version of this weapon to fail by the same margin. The United States Navy will adjust its doctrine, its detection thresholds, and its interceptor protocols based on what was learned in those 14 seconds. But doctrine updates take time, engineering solutions take longer, and adversaries do not wait for defenders to adapt before developing the next generation of threat. The Persian Gulf is not returning to a stable equilibrium. The strategic tension that produced this engagement is not dissolving. The military, economic, and political pressures that drove Iran to fire a Mach 15 weapon at the most recognizable symbol of American naval power are still present, and in several respects, still intensifying. The ocean, as it was put in the aftermath of this engagement, is no longer a sanctuary. The distance between an Iranian launch position and an American carrier strike group is no longer the protective buffer it once appeared to be. The physics of hypersonic weapons have collapsed that buffer in ways that fundamentally alter the risk calculations on both sides. What this engagement tells us about the future of military confrontation in the Persian Gulf and beyond it is something that strategic analysts, defense planners, and political decision-makers will be examining for years. But the fundamental lesson is already visible. The era in which a technologically superior Navy could operate in a contested region with a comfortable confidence that its defenses were categorically untestable is ending. Not ended, ending. The margin still exists. American technology still performed. American decision-making still prevailed. But by 0.23 seconds. And in geopolitics, as in naval warfare, the most dangerous moment is not the one where the defense fails completely. The most dangerous moment is the one where the defense succeeds, but only barely, and the world draws the wrong conclusion about what that narrow success actually means. Because the next weapon will be designed to eliminate those 0.23 seconds. And when that happens, the outcome will not be determined by better radar, better algorithms, or better probability calculations. It will be determined by whether the world paid close enough attention to what almost happened before it did. I'm Dr. Margaret Sullivan. Stay alert, stay informed, because the next engagement may not give either side 14 seconds to decide.